Good morning everyone and welcome back. In a previous video I demonstrated how you could use a digital twin to support structural health monitoring, and then I used a cantilever beam as an example. In this video I will use a Nevada RK4 rotor test rig to demonstrate condition monitoring supported by a digital twin model created in FEDEM. And here you see both models running at critical speeds. First the physical model of the test rig, and here you see the virtual model of the test rig. The RK4 test rig by Nevada is made to demonstrate rotor unbalance, shaft rub conditions and instabilities due to oil whirl and oil whip. But in this video I will only demonstrate rotor unbalance. The RK4 test rig is very flexible and can be configured many ways. But basically it consists of a frame supporting a motor, gear unit, two bearings keeping the axle in position. It also has some brackets with the proximity sensors that can measure the displacements of the axle during acceleration through critical speeds. You can also add one or more inertias to the axle system. The purpose of this video is to teach you about rotor dynamics and condition monitoring, based on a physical test rig and its digital twin model. Rotor dynamics is commonly used to analyze the behavior of rotating structures such as jet engines, windmills, automotive and marine drivetrains. Condition monitoring is the process of monitoring machinery such as this RK4 rig in order to identify failure modes or future failure modes, and it's a component of predictive maintenance. This is the agenda for this video, and the first point on my list is resonance and critical speeds in axial systems. A natural frequency or eigenfrequency is the frequency at which a system tends to oscillate, and a rotating system like this might have several eigenfrequencies. And when you accelerate the rotating system, you might have resonance at certain speeds, termed critical speeds. And that's when the input rotation speed is matching one of the natural frequencies. Then you will get resonance. And you can see here what happens. The dynamic amplification factor increases until you reaches the critical speeds, and then it relaxes again. And this shows why you should not run a rotating system at critical speeds, because you might harm the rotating system, you might ruin the bearings or any other component in the system. Next point on my list is to show how you can do a physical test of the RK4 rotor system. Here you see the RK4 test setup. It has a motor controller that is using a sine sweep function to accelerate the rotor system through critical speeds. And then you have a data acquisition system which is sampling the proximity sensors and transfers the data to the laptop, where you have some proprietary software which is visualizing the responses from the sensors. And here again you can see what happens when you accelerate the RK4 to the first critical speed, which is matching resonance frequency number 1 at 32 Hz. This is recorded by a Photron high-speed camera. And here you see you reaches the critical speed, the first eigenfrequency, and you get a huge amplification factor. And then it relaxes again at over critical speeds. Then I will say some words about how to select the sample frequency. It's especially important if you're running a digital twin setup that you are using the same sample frequency in both the physical and virtual test. Assume that we have a sine type of input signal with a maximum frequency of 1 Hz. If you then use a sampling frequency of 1 Hz, you will see that the output signal will appear to be a constant signal, which is obviously wrong. Then, if we increase the sampling frequency to, for example, 7 samples per 4 periods, the sample signal aliases to a frequency less than the original signal, and you will output 3 cycles instead of 4. That means the frequency will be wrong. Then if you use Nyquist criterion to select the minimum sampling frequency, you will sample each wave or period with 2 samples. And then you will get the correct output frequency and the same number of cycles, but the original signal or waveform will be not corresponding. The waveform will be wrong. Then if you choose a sampling frequency which is 10 times higher than the maximum input frequency, then you will capture both the correct frequency and waveform in your output signal. And that is my recommendation, to use a sampling frequency both in physical tests and numerical simulations which are 10 times higher than the maximum input signal frequency. Rotor dynamic simulations are usually performed in the frequency domain. But as you all know, physical tests are performed in the time domain. And also all loads are acting in the time domain. And for me, it's easier and better and also more efficient to run the digital twin simulation in the time domain as well. And now I can show you how you can set up and run a rotor dynamic simulation in FEDEM in the time domain. Here you see the FEDEM user interface. It consists of the graphic window. You got a part browser, and you got a topology browser and a property window here. And as you can see here, this finite element assembly consists of 15 component FEMs which are meshed and imported from NX. In FEDEM, you position all the 15 component FEMs in a global coordinate system. In this case, all component FEMs were meshed in a global coordinate system already, so I didn't have to position them in FEDEM. Then I applied a motor defined by 2 revolute joints and an input torque from a control system. And the main axial is spinning through a universal joint here. And here we have 2 bearings, the light blue ones. And the properties of these bearings are assigned to free joints. And these free joints have 6 degrees of freedom that can relate to both Cartesian and cylindrical coordinate system for correct representation of nonlinear damping and stiffness. In addition, you have sensor brackets here, where proximity sensors are located on the physical model. But here you can add additional sensors as well. And we have a flywheel with an off-center mass that can be introduced. And the overall support structure is fixed to ground by using rigid constraints or rigid joints. The RK4 digital twin model is instrumented with 1 tachometer and 6 proximity sensors, modeled as relative sensors in FEDEM. And these are measuring the radial deformations at 3 points in 2 different directions. And these can be directly compared with the outputs from the physical tests. The bearing loads and also the flywheel displacements are not measured on the physical test rig, but these are measured in the simulation model. So in that way, we can do condition monitoring based on the digital twin instead of the physical test rig. Here you see the input torque driving the RK4 digital twin model. And this is how the torque is calculated. I have the reference speed, which is the same reference speed as used in the physical test. And then I have a feedback of the actual speed on the digital model measured by this sensor, which is a tachometer. And based on the deviation from the desired speed, the controller will set up an input current which is driving the motor, modeled by a low-pass transfer function. And the calculated torque here is applied directly to this torque symbol here. As you can see, it's a control out. And this one is then driving the simulation model. However, this control system is only used when I benchmark my finite element model or the FEDEM model. When I want to run this in a digital twin mode, I use the reference speed, which is the input to the physical test or the measured speed in the physical test to drive this rotor system directly. And the input speed then, measured input speed, is then applied directly to this revolute joint on this model. And then I'm bypassing this controller. Here is the digital twin model in FEDEM of the RK4 test rig. And some of the parts here are hidden. First, let's have a look at the mode shapes and frequencies that causes the resonance problems. First, we can check bending mode number 1 of the axial system. It has an eigenfrequency of 31.9 Hz. Then we can check out the next frequency, which is a horizontal mode shape. And in FEDEM, it has almost the same eigenfrequency as the vertical eigenfrequency or mode shape. And these are the two modes that cause resonance problems. There are also additional torsional modes, which we don't care about right now. You can run rotor dynamic analysis in FEDEM, both for engineering purposes and in a digital twin context. And here you see the control system I described, and this is the output from the control system, which is attached to the input torque here. Let's find the right symbol, that one, and you see I'm applying a torque here. When I want to prepare this for digital twin simulations, I select none here because I don't want to use the output from the control system. I simply want to use the measured input rotation from the physical test rig. And then I use this revolute joint instead, and I apply a reference speed here, which is a prescribed velocity. And that is my input. And then I can run a dynamic analysis. And in advance, I can select the outputs, which I can check out during the simulation to verify that my simulation is running well. So I can select some graphs here, and I can select bearing loads, which are typically outputs from a condition monitoring simulation, as well as virtual strain gauge outputs. These are my rosettes, which I can select. And then I choose Windows Tile. And then we can check out the results while we are simulating the digital twin. The graphical performance is a bit slow here due to the fact that I'm recording a video simultaneously. But here you see the input axial speed is approaching my eigenfrequency, or the two eigenfrequencies, at roughly 32 Hz. And then I expect these bearing loads to increase due to resonance, or I'm approaching the critical speed. And these are my rosette stresses. And here you see my rosette, which gives me in real time the strain time histories that I can use for fatigue analysis. And you can see the animation, and you can also see the results plotted simultaneously. And here I can select my proximity sensors output, which are directly comparable to the outputs from the physical test. And here you see the resonance at 32 Hz after almost 8 seconds. The orange curves here are actually outputs from the physical test. And if you compare them, you can tell that I got resonance at a critical speed of 32 Hz here, and only one resonance peak. While the physical test gives me an output or a resonance peak at roughly 31 and 32 Hz. The reason is probably that I have a model which is not fully representing the physical model. It might be that the physical model is not clamped as it should be. It might be that the sideways stiffness is too low, indicated by the first peak here, and that the vertical oscillation or eigenfrequency of the real system is a bit higher than the horizontal eigenfrequency. So here you see all the results simultaneously, and you can now animate them after the simulation is completed. In this animation, you can see that when the applied input rotation is reaching or matching the eigenfrequencies on my system, I got critical speed and resonances, as you see here. And you will see that influences both the proximity sensors, that means the radial displacements of the axial. You can also see it on the stress rosettes, the strains and stresses from the strain gauge here, and you can see it on the bearing loads. And these are sensor outputs, the bearing loads and the rosettes, that are not available directly from the physical test rig. And that is why FEDEM is really well suited for condition monitoring. When the FEDEM model is benchmarked and optimized for maximum simulation performance, then you can prepare it for digital twin simulations. And then you got several options. If you're familiar with Python, you can use the FEDEM PyScript or API to run FEDEM from your own Python script, which might have user interfaces created in an app like Streamlit in order to visualize curves, 3D animations from the FEDEM simulation in a web application. An alternative is to go to File Export and then export a digital twin model. And here you can export apps for streaming and batch execution. You can also create an FMU, and that is my recommendation, because if you export an FMU, you can include it in co-simulations in programs like ANSYS Twin Builder or Siemens AIMESIM, or in your own Python code, for example. And the benefit with FMU is it's a standard, so it's applicable in many frameworks, IoT frameworks. However, there is one thing you have to remember, and you have to go to the functions, and in an FMU you have to predefine the inputs and outputs, and that's what you do here with the functions. Here, all the functions or the results which are tagged sensors are output from a FMU, and those who are marked external, which are those actuators used as inputs to the digital twin model. So here you can see I will have one input to my FMU, which is the reference speed from a physical test, and I will have several outputs here, which are representing this rosette outputs I showed you, and also the proximity sensors on the bearings and other brackets. So this has to be prepared, and then you can run FEDEM as a digital twin. The next point on my task list is related to model validation or model tuning. And the question is, how well does my digital twin model has to match the real physical asset? It's hard to answer that question, but what you should intend to do is to model the physical asset in its mint condition. That means in a condition without defects. And then when you start simulating the model, you can plot the expected or simulated response versus the observed real physical measurements. And ideally, you should then have to a 1-to-1 ratio, a linear curve. But usually, due to wear and tear and damage and defects, after a while, the observed results, the physical measurements, will deviate from the simulated performance or results. And then you know that there is some kind of defect in your physical asset. Let's have a look at my model again. The only way I can validate my FEDEM model of the RK4 test rig is to compare the outputs from the physical and virtual proximity sensors. And here you see that the amplitude, that means the radial displacements of the axial, is roughly the same. It's approximately 0.4 millimeters, and the resonance is also acting at the same critical speed. That means 32 Hz. I can't compare the outputs from the virtual strain gauges and the bearing loads because I don't have physical force transducers or rosettes on my physical test rig. But that's also the idea with a virtual model or a digital twin, is to provide additional outputs from virtual sensors that are free of charge. So these can be used as inputs to fatigue analysis, and this can be used in traditional condition monitoring of bearings. However, these are more sensitive to errors in the model. There are different ways to use a digital twin model in condition monitoring of a physical asset. First, if you have an expected linear relationship or a linear behavior of your asset, then you can model the asset in its mint condition, and then you can compare the simulation results with the observed or physical test results, and you should have a one-to-one relationship. That means a linear relationship. However, some physical assets have a nonlinear behavior, and then you might need to update your finite element model or digital twin model. And there are different algorithms in machine learning and analytics that can assist you in updating the model. And then you will have a more accurate prediction from the digital twin model when the physical asset is approaching end of life or is having a nonlinear behavior. In my course, I'm using my RK4 twin to verify what happens when you run the test beyond 100 Hz and you hit the resonance frequencies or the critical speeds. And that is when you meet the two bending modes of the axial system at roughly 132 Hz. Then I want to identify the frequency and shapes of the three lowest RK4 axial modes. Sometimes the torsional mode can also have an impact on the life of a clutch or a gear unit. There might be torsional vibrations that can amplify the input torques and damage the driveline. Then I used the model to select a proper sampling frequency that is capturing all the oscillations. And I used it for tuning a PID controller that gave me the wanted simulation speed as in the physical test. Then I used it to match or verify the physical results and run digital twin simulation that gave me additional results and information from the digital twin. And then our digital twin model also reveals error sources causing deviations between the test and simulated results. And I had to verify especially the damping, and I had to verify the physical stiffness in my test rig, especially in the bearings, due to the different eigenfrequencies in the horizontal and vertical plane. So I identified that there were some issues on the physical test rig. And then I can use it to compare and evaluate methods to avoid structural resonance and damage in a driveline. And last but not least, I want to teach the students about critical speeds and resonances in rotating systems and why they are dangerous. And of course, this is a case in my course demonstrating condition monitoring. The last point on my task list is actually a student exercise. The RK4 test rig is too large to be carried around, and I prepared a Bentley Nevada RK4 rig, which is smaller, and I've also prepared a digital twin model of it in FEDEM, which can be used in digital twin based condition monitoring. And this is how it sounds like when you run the test rig through critical speeds. You can hear that the system is passing through the critical speed twice when I accelerate it and when I deaccelerate it. That's all, folks. Thanks for watching, and I'm now preparing videos demonstrating how you can apply digital twin models for condition and structural health monitoring in an IoT system that is based on Python and Streamlit. See you soon. Bye bye.